All right, recording is rolling. It is Monday, September 19th. Yeah, so I have not seen you guys in a few days now. We were just last time I saw you back on Wednesday. You guys remember you guys did that 10-part mini labs? Looks like let me throw it here real fast. Right, it was these. We were going through these, trying to figure out how the forces work. You guys had those spring scales and those lab weights. Right? You were trying all different configurations of these forces. Well, what if I do this with them? What if I do this with them? Right? And so it's mostly debriefed that with you guys. We were just starting to get on a roll, and then yeah, been covering some tests last few days. Right. So what we got here? Let's go top to bottom here. School pictures. Yeah. So hopefully you guys saw that. I got an email back on Friday afternoon and posted that to Google Classroom that today is picture day. So that's through your English classes. If you do not have an English class, you might need a couple of guys, then go either during lunch or between classes or, well, I guess after school or just you have to get a pass from one of your teachers at some point. Okay. So picture day. Projectile motion. Your quizzes are back in your folders. So if you want to get those, remember, if you want to do corrections, you can, whichever ones you missed, handwrite out solutions. If it's a graph, draw the correct graph. If it's some kind of equation type problem, then set it up and then go through the process and solve it. Right, so I do have my top scientists printed out, but I must have left them home, so sorry about that. But it is a full list, so you guys will get to see that tomorrow. You guys did really good on that, which is really awesome because this is one of the hardest topics for a lot of students is projectile motion. Okay. Right, so yeah, over last few days, I haven't seen you guys. Some things that you may have seen are these flip books. Right, so with your covering teacher, right, I left you guys a set of flip books here. So this is you can apply your physics knowledge, kinematic knowledge, plus some imagination. And what's I got here? Just throw a few here. So I did a whole Google. I posted a video to Google Classroom of a bunch of these, so some really good examples. Right? There's some recent examples. I've got one's from Cole. See, this one's from Brody, water droplet. Got a B from Isabella. B, yay, happy times. So that's pretty fun. Hopefully you guys were able to use your imaginations and put those together. The other thing that I threw at your covering teachers was this template right here. And I didn't really explain this because it was actually curious to see if you guys could figure this out or think about this a little bit. But here, I'll do a quick crash course with you guys. Right, so here, let's imagine for a moment. It's like back in the 1960s, and you guys are scientists and engineers working on the Apollo program. You're gonna send astronauts up to the moon. Do you guys have one of these conveniently in your pocket? Not really, right? These digital calculators don't really come around for a while. But we need some kind of math. We're probably crunching lots of numbers to get astronauts to the moon. So what are we using? How about slide rules? You guys ever seen like a slide rule? Okay, so this actually is a slide rule, but it's just in circular form, which is actually a little bit better design. I'll tell you what, if you threw one of these into the hands of like some astronauts and some engineers back in the 1960s, they were like, "Whoa, this is so much better than you know what we're in." So what's going on here? So you can use this to multiply, divide, and take roots. I'll show you guys how. So the numbers are spaced logarithmically. See the inside numbers and the outside numbers. Right? So they can match up. So the 3, 4, and 4, the 5, and 5 match up all the way around. Okay. But if I rotate this thing, then what you'll see if I match this 3 with this 1, treat this as a ratio, like 3/1. It turns out that the ratios are also the same all the way around. Okay. So 3/1, 6/2, 9/3. What's this? 1.2/4? I know 12/4 is also equal to 3. Right, so one of the tricks with this is that you have to float the decimal point. Yeah, you'd have to keep track in your own mind of like, okay, where's a reasonable place for the decimal point to go? Right, because the digits are only 1 through 9. Right. Right. So how can you use this to multiply? Well, if all the ratios are the same, for example, if 3/1 is equal to let's do 6/2, right? 3/1 is equal to 6/2. Like all the ratios are equal. You can set up equivalent fractions and solve division really quick. For example, if you're learning what is 6/2, just for example, what is 6/2? Well, since it's equivalent to 3/1, whatever the one is, like as the denominator, that's sort of like pointer. It points to the answer, doesn't it? Right? It's just equal to 3. Okay? In fact, the ratios of any numbers all the way around this ring are all equal to exactly 3. I could shift this and do something weird, like, I wonder what is 2.4 divided by 5, or what is 24 divided by 5? However you interpret that. Ew, I don't know, that's something weird. But the yellow one points to the answer. Okay, it looks like it's about 4.4-ish. Let's check that real fast. What is 24 over 5? Oh, it's 4.8. Boom, done. Right? So, actually, whoops. Sorry, 4.4 is over here. It is pointing to 4.8. Right. So you can multiply and divide with these things. You can also do square roots, and you only need one of the circles to do that. So, right. Guys, what is the square root of 9? 3, right? Okay. And since this is logarithmic, you guys know how exponential logarithms work. What is the square root expressed as a power? It's 9 to the power of half. Right. So if you use 1 as like the home base, remember it was like the pointer before. You look at where the 9 is, which is right here. You say like halfway. What's halfway around? What's halfway around here to here? Oh, it's 3. Okay. How about this? What's the cube root of 8? 2. Right. Hey, cube root, is that like a power of a third? So if I split this into thirds, right? Here's 1/3, 2/3, 3/3, right? Right. What's 1/3 of the way around? Oh, it's 2. Right. So you can do roots of those 2. Right. What's the square root of 3? Square root of 3. It's like 1.73. 1.73. The square root of 3 is 1.73. Let's try it to that. 1, 3, square root. What's halfway in between? Right about there. Oh, it's about 1.7 something. All right. So good. All right. So that's a quick crash course on slide rules and the circular version of that. Okay, but gotta get to. You know what? You guys had this mystery cup challenge. You guys figured this out yet? How the mystery cup works? Okay. Let me remind you guys and give you guys another day to think about this. So take this cup, okay, which has some holes in it. Okay. You fill it up halfway with water. It holds the water. You fill it up all the way, and the entire cup drains. This cup's been around this design for thousands of years. But how do you make it? And so you guys be thinking about that. All right, now let's get to today's stuff. Today's going to be lots of notes. So I got you guys roast days. You can full focus on this. Right? Now, while you guys are getting your notebooks out, get oriented. Let's take a look at Newton's laws of motion. At some point, I got to flash these up here, go over these. So I think now's a pretty good time. Okay. So there are these 3 laws of motion that govern everything in the universe. Well, until you get to general relativity, but hold up on that. Okay, so first law of motion is also called the law of inertia. Hopefully you guys did these like back in middle school. Hopefully it's just a refresher from some science class you guys took back in the day. Okay. So first law of motion, also called the law of inertia. An object at rest will remain at rest, right? Until there's an outside force acting on it. So nothing's like, if I just sit right here, it's just not going to spontaneously jump off my desk, right? Okay. But if I put a force on it, right? Okay. Oh, and also this, an object in motion will maintain its velocity. You guys know what velocity is. It has 2 components to it. Speed, which is the magnitude, and direction, because velocity is a vector value, right? Okay. So speed and direction, okay. Until again, an outside force acts on it. Okay. So a classic question I always ask is, the Voyager 1 spacecraft was launched back in the 1970s, right? It's just been going for decades. Right? Is there, can it just like run out of fuel and just like come to a stop in deep space? That's kind of what would happen to your car, right? But your car has lots of forces acting on it, lots of frictional forces. No, so what's keeping this thing going? It's still going. What's keeping it going? Just inertia, right? Just the fact that there's no force to change its motion, right? If you're in deep space, you're going with some speed, some direction, you're just gonna keep going forever. Same speed, same direction. The only reason you would ever speed up, slow down, or change direction is if there's an outside force. If there's no outside force, you're not going to change what you're doing. Okay, that's law of inertia. Okay, you guys got that? Okay. Newton's second law of motion. Oh, okay. So this is one that you can probably. Here's my favorite version of Newton's second law of motion. Skip past the words. I like this fraction equation right here. What is the acceleration on an object? Because you guys have been measuring acceleration for the last few weeks. You guys did the car and ramp lab. You guys know acceleration is rate change of motion. But now we're getting to what causes acceleration. And the answer is a net force, right? Now, there might be lots of forces on an object, right? Like this right here, I could put like, these different forces, but there can only be one like net motion of it, right? There can only be one acceleration. So it's really the net force I care about. So if you have forces acting all different directions, I have to do some components and add the X component to the Y component, blah, 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 right? Once you figure out what is the net force, almost as if there's just a single force acting on it, right? and then divide by the mass of that object. That'll tell you what its acceleration is, both magnitude and also direction, right? Because force is a vector, has the direction. Acceleration is also a vector, has the exact same direction as the net force, right? Do you guys see if you triple the net force, what happens to the acceleration? It also triples. You guys see that? That's a direct relationship. What if you triple the mass? All else equal, what happens to the acceleration? Like if I had 1 kilogram, put a force on it, it's going to accelerate. If I have 3 of these guys and put the same force, isn't it going to accelerate less? Shouldn't be a third as much. And that's like an inverse relationship. You guys see that? Okay. Now, more often you'll probably see it written in the non-fraction form, F equals ma. Okay. I like the fraction form. I think it explains the cause effect a little bit better. But you might be able to feel both, right? Right. So forces cause accelerations, right? Right. And then if you want it spelled out in words, if you're a more wordy kind of person, acceleration of an object is directly proportional to the net force. That's what this is. And also inversely proportional to its mass. There you go. Newton's second law motion. Boom, just like that. Okay. Hey, do you guys see anything about velocity in Newton's second law motion? Do forces cause velocities? No, just accelerations, right? Interesting. And then third law, I know for sure everybody's heard this. You guys ever heard like equal and opposite reactions? Right? So spell this out a little bit more technically. For every force on object A by object B, there's a reactive force equal in magnitude and opposite direction on object B by object A, right? So got this sitting here. If I'm pushing on it, right, then it's pushing back on me with exactly the same force, right? So and there'd be no way to ever break that, right? Whether it's accelerating or not. Right? If there are 2 objects that are pushing on each other, you have the equal and opposite forces between those 2 objects. Okay. All right, guys, set so far? Guys, all right? All right. So we're going to take the rest of class and probably more class another day to do some free body diagrams. All right, guys, ready for free body diagrams? So I'm going to flip the screen over, and we're going to do the rest of the class as a PowerPoint because I think it's a pretty efficient way to do this. Where's share screen 2? Here we go. Let's present this. All right, free body diet. Yeah. Okay, sure. Let's go with that. What's this? No, I don't want subtitles. Okay. Free body diagram. Okay, so there you go. There's a nice definition. A diagram showing all the forces acting on an object. Okay, that's basically all it is. Right? We just got an object, and we're just going to label all the forces. Notice those forces are drawn as vectors, right? Like little arrow vectors. Right? And I've also labeled the forces there, right? So you know what force is what. Right? There's going to be some FRQ you guys are going to get in May. It's going to have you draw free body diagrams. You're going to have to label what the forces are. Right? Right, so AP always has this. Scratch that. Right? Draw force vectors that represent relative magnitude and direction of each of the forces. So my example here, like here's a free body diagram. Maybe just a block, just at rest on a table. Right? It has a weight that's pulling down. So anytime you see mg, that's mass times gravity field. I usually represent weight that way. You can also do F sub g, like force due to gravity. Right. And then does anybody know what F sub n is? What the n stands for? Right. Normal. Yeah. So it stands for the normal force. Right. And what does the word normal mean in mathematics? If 2 lines are normal, they're what? Perpendicular. So here, let me do this. I'm gonna flip my screen over here just to show you exactly what you guys just saw. The free body diagram. That's it. Right. See this weight right here? Could you imagine that it has a gravity force pulling down? Right. And hey, if there's a gravity force pulling down, if that was the only force, wouldn't it just be a free fall? Like if I dropped this to the edge of a cliff, just be the only force on it would be its own weight, pulling straight down. Right. But here it's in equilibrium, right? Equilibrium, there's no acceleration, right? Because there's no net force. If acceleration is 0, the net force must be 0. So it can't just be its own weight. Hey, I bet there's a support force from the surface holding it up. That must be equal in magnitude to its own weight, right? So, and do you guys see how like the surface is like parallel to the ground, right? So the normal force, normal means perpendicular, is always perpendicular to the surface. In this case, it happens to be vertical because the surface is horizontal, right? Is it? But if I did something like got any kind of Here we go. If I gave any kind of incline, get textbook up here. Right. If I put this on an incline and start tipping this, right? The more vertical this gets, if this gets almost like a wall where the vertical, if it's almost vertical, the wall would be. Right. You guys imagine there's a very small, like surface force pushing back on it. In fact, that surface force probably increases the closer it is to like a flat surface, right? Okay. Just getting you guys thinking right now. You guys are going to see this shown in a diagram later. In fact, it's sort of on that poster right there. Kind of what I'm getting at, like force on an incline. So we're not quite there yet. Just trying to plant some ideas in your mind. Okay. Okay. So let's go back to what we got right here. Okay. So there's a weight pulling down. There's the normal force holding it up. Right. Those are balancing out in this case. Okay. I've got this line that says like for AP. So, you know, I guess every textbook has a slightly different convention how to do this. Actually, I like AP's convention, so I'm just going to do this anyway. But see where it says always connect tails of vectors to the center of mass. See, there's like a center mass dot right there, right? And draw the force vector extending away from that object. Now, there might be sort of an exception to that when we get to like rotational dynamics, and you know maybe there's like a friction force acting on this side of the object, and then there's something else acting over here, right? But until we get to that point, we're just going to connect everything to the center mass dot, right? So we're not worried about like rotating that object yet. Okay. All right, you guys good so far? Okay. So see how the vectors are connected to that center mass dot. Okay. See if you don't do that, then AP will count off. Okay. And some of my textbook solutions that I wrote a few years back, some of my old materials, I may not follow that convention. So you know in your mind, like, okay, this is just like way I learned it way back in the day. Okay. Forces are measured in newtons. Right? You guys know that? Okay. Remember, those red arrow vectors right there are force vectors. They're not velocity vectors. They're not acceleration vectors, right, which are different concepts, right? Velocity is in meters per second, and velocity is, I mean, that's just relative anyway. You can only measure velocity relative to like something else, like, oh, that nearby tree or something stationary, right? And acceleration are caused by forces, and they're in the same direction as the net forces, but that's like meters per second squared, right? So that's not right. So you're interested in just force vectors. Okay, guys good? Good. All right. Next slide. Block at rest on a table. Okay, well, you just saw it, right? So there's two forces. There's the weight pulling down, and there's the normal force acting up. Boom, boom, just like that. Okay, you just did that. You guys good there? Oh, yeah. Yeah, it is. It's good call. That is a good idea. It is posted to Google Classroom, so you guys can go in there and check all these out. Yeah. All right. How about this? And see if you guys can draw these before I show you the answers, because if you guys are getting these, then that's a good sign. Okay. What if there's a block at rest on a table? Now, at rest, what do you know about the net force already? Zero. So there's got to be zero net force, right? Okay. Pushed horizontally. Ooh, right. But not with enough force to overcome the friction between the block and the table surface. Okay. So block is sitting there at rest. There is a horizontal force pushing it, like an applied force. But there's probably some kind of friction force, still locking it in place. Okay. I'm thinking 4 force vectors. I'm trying to give you guys an opportunity to draw this first. Okay. Okay. Did you guys draw a weight down? Okay. I mean, that's going to kickstart everything. If you don't have that, then nothing else can really be there, right? There's going to be the support force from the table, the normal force, right? And you know, if it's a horizontal table, I mean, I guess it's implied just horizontal table, then right, those two are going to balance out, right? Right. So if it's like 7 newtons of weight, it'd be also 7 newtons of normal force. See how they're the same magnitude, right? Then there's going to be this applied force. I call it F sub push. You could call it that. You can call it F sub applied. Okay, like a pushing force. Okay. Now, if I just did that and walked away, would that block right there, as it's shown, be in equilibrium? It would not. It would be accelerated, wouldn't it? Right? Not just moving. It would actually have to be like either speeding up to the right, or it could possibly be moving to the left but slowing down. And it actually would be ambiguous as to which one of those it is. Right? It might be either of those. It might be speeding up to the right or moving to the left but slowing down. Right? And you wouldn't know which one of those it is just by looking at that picture. But we need one more. Hey, what's that? What's that? I know it's better. All right. Friction force, F sub FR, friction. You guys see how it's like balancing out with the pushing force? Right? You guys see it? Do you guys also see how the friction force is a smaller magnitude than the normal force? Right? That's almost always true. In fact, the last time I saw you guys back on Wednesday, I was just starting to touch on that idea. That the ratio of the friction force to the normal force is is an important concept in physics. It's called the coefficient of friction, right? Well, if you have static friction, like here, the pushing force and the friction force haven't built up enough to overcome that static friction yet. So maybe you could still push harder, and the friction force would still be building up until at some point it would break that friction, and then it would start sliding. In that point where it breaks the friction, if you take the ratio of friction to normal force, right, that would be called the coefficient of static friction. Okay. Now, if this block it does happen to be moving at constant velocity, which would still be equilibrium, guys, is constant velocity equilibrium? Yeah, because there's zero acceleration. It'd be zero net force, right? Which might look a lot like that, right? Then you could just take friction force to a normal force, just whatever that ratio is, and that's called the coefficient of kinetic friction. Kinetic is in moving, right? Good. All right. And and coefficient of friction is a material property. So it's like, okay, if you have like maybe a weight made out of some kind of metal on some kind of like paper, maybe out of surface or wood or whatever it is, right? Whatever those materials are will determine what that coefficient is, right? And then you can determine what the friction is. Right? Block on a table, pushed horizontally so that the block moves. It's moving. With constant velocity across the surface. With constant velocity. Here you got some very strong hints, just the last slide, about what this should look like. You guys are drawing this in your notebooks. Take a quick trek around the room. See who's going to get this. He's going to get this one. All right, so block is on the table. It is being pushed. It's being pushed at constant velocity. All right. Did everybody draw the weight? Okay, so there's a gravity force pulling it down. You can label it mg like I did, or you can label it F sub g, like force due to gravity. Okay. Did you guys have a normal force holding it up? So it's not like plummeting down. Right? It's not in free fall. Okay. Now it is being pushed, and there is a friction force. Also, it's constant velocity. That's an important tidbit of information too, right? Because what does the constant velocity tell you? No acceleration, which means zero net force. Does that mean that the applied force and the friction force still should balance out? In fact, does that free body diagram look exactly like the one on the last slide? It sure does, doesn't it? Right? In fact, if all you had was that free body diagram, it'd be kind of hard to tell, is the block at rest or moving at constant velocity? And unless you were told that diagram kinetic friction or told something about that. Okay. Exactly. Yeah, you guys hear that? All right. So if these two forces were unbalanced, and say one was bigger than the other, right, then there would be a net force and it would be accelerating, right? Now it might be speeding up, it might be slowing down, right? I bet if you pushed harder than the friction was, it'd probably be speeding up to the right. And if the friction was greater than the applied force, like if there's more force to the left, do you think it would be slowing down as it moves to the right? Be moving to the right, slowing down, right? If the friction force is greater. Right. All right, you guys ready for the next slide?
So how do you know if it has constant velocity versus if it's at rest?
It's the arrow. Okay, yeah. That's a great question. How do you know if it's moving at constant velocity versus at rest? Right. If you just look at the free body diagram, it's ambiguous. You can't know. Right? Unless you were told some detail like the friction is like static versus kinetic. If it was static friction, it'd have to be at rest. If it was kinetic friction, it'd have to be in motion. But if you're just told friction, then yeah, you would not know just by looking at that diagram. Right? Because if I go back to the previous slide, the block at rest, boom, it looks exactly the same, doesn't it? Yeah. So whether there's velocity or not is ambiguous. Okay. But you guys have kind of known that anyway, because you guys remember if you're in a car going 70 miles an hour, just cruise control, it's your constant velocity, you can't actually feel that. because from a physics point of view, right, there's still zero net force. Right. Block on a table, ooh, push horizontally so that there is a net force. Right. Let's do this one a little bit faster. There's probably more than one right solution on this one, right? So, but there's a weight down, there's a normal force holding the block up, right, preventing free fall. Right. You guys have an applied force and a friction force, right? Now, the way I drew this is I have more pushing force than friction force. But if you drew yours with more friction force than pushing force, that would also be valid for that setup, right? As long as they're not balanced, right? Okay, guys good? Ready for the next slide? Okay, okay. On a table, push horizontally. There is a net force. Yeah.
So do we always assume that there's friction?
That's pretty common, right? Yeah. Let's see. I guess I guess it depends on like the context of the question, right? So sometimes it'll specify, it'll say like a frictionless surface. Yeah, and sometimes it'll say there is friction, and I guess if it doesn't, well, but we'll see when we come across it if there's a situation like that. All right. Ooh, rock and free fall with no air resistance, right? Which is our normal go-to assumption anyway, right? That there's no air drag. Right. So go to the edge of a cliff, drop a rock. What's that gonna look like? Did you guys draw a weight pulling down? Did you guys draw anything else? No, that's it. We're done. That's the whole thing. Boom. Right. Hey, what if you did this? What if you took that rock and you chucked it horizontally off the edge of the cliff? Right? And at this point, the rock has left your hand and it's moving in like a parabola motion. What would the free body diagram look like for a rock moving in a parabola motion? Would look exactly like that? Yes, it would. Yes, it would. Right. As long as there's no air drag, that's all we care about, right? Right. It doesn't matter which direction it's moving. All it matters is what's the force on it. Okay. Okay, here we go. Rock and free fall with air drag. But let's say before it's reached terminal velocity. Ooh, I guess you guys need to know what that is. I bet some of you guys do. Guys, what is terminal velocity? So it's like the final velocity of reach in. You guys think that as soon as you drop the rock, there's probably like negligible air drag anyway, just because it's not really moving that fast. Okay. But you guys think the faster it's moving, the more the air drag is going to pick up? Okay. Actually, it turns out that the amount of air drag is proportional to the square of the speed between the rock and the air. Right. So yeah, the faster it falls, the more the air drag is going to build up. Now, do you guys think that at some point the air drag is going to build up to match the weight of the rock? And at that point, would the rock be in equilibrium, which means that it just does it stop in midair? No, it just moves down how?
Constant velocity.
Constant velocity, yeah, and it can't pick up any more speed, right? But then the air drag wouldn't pick up either. Okay. So we're not quite there yet. That's probably a slide coming up. But let's see what you guys got for this one before. All right, so you guys got the weight pulling down, right? So it's falling down faster, 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 right? And then the air drag's building up, but see how the air drag hasn't built up to match the weight yet, right? Okay. So is that rock right? Let's see if you guys are following. That rock right there that you guys are seeing right on that slide, is that rock in equilibrium? No. Ew, it is not. Okay. There's a net force, right? So is that rock still accelerating? Yes. Right. Is it accelerating at the full 10 meters per second squared? No. Right here. Okay. All right. So what if let's take some numbers real fast. Let's say the rock let's say it has a mass of 1 kilogram. 1 kilogram. What's its weight equal to about? About 10 newtons, right? Because m times g, right? Here, mg, 1 kilogram, 10 meters per second squared. So 1 kilogram weighs about 10 newtons on Earth, right? What if the drag force is built up to, does it look about half the length, maybe 5 newtons? Guys, what is 10 minus 5? 5. So there would be a 5 Newton net force. Now let's go to Newton's second law of motion. If there's 5 newtons net force acting on 1 kilogram, what's the acceleration? It'd be 5 meters per second squared, right? A equals F over m. Yeah, what are you gonna say?
So at terminal velocity, the forces would be equal, right? The normal
force,
because it's not accelerating anymore.
Or the drag force would match the weight. let me see if that's the next slide coming up. I think it is. Ah, it is. It is. All right. All right. So see if you guys can figure out what Alexander was just saying, right? Well, about that situation right there. Right. So now the rock's been falling for a few more seconds, falling faster, faster, faster. So remember that drag force is proportional to the square of the speed. So the fact that it's going faster means that drag force picking up. Okay. Now it has reached terminal velocity. Okay. Did you guys just draw the same weight still acting down, but now the drag force is picked up and is balancing the weight? Right. So now it's just going to go down at constant velocity all the way down the ground. Right. Let's go that. You know what I want to do with you guys? Let me flip the screen here. Okay. Let's do a little side thought on that situation. So flip my screen. Come on. Here we go. Okay. I want to do a new graph with you guys. Actually, maybe I'll do a paragraph side by side. Okay. Let's say free fall, no air drag, and let's say free fall with air drag. Okay, you guys remember we've been doing those three graphs over. Oh, that's thing. Come on. Okay. Sorry, here we go. Okay. Free fall. Okay. So let's look at these two different ways to consider this. Okay. I just wanted to focus on one of those three kinematic type graphs, which is just the velocity versus time. Okay. So you go to the edge of the cliff, you drop a rock. So that's the scenario. Go to the edge of the cliff, you drop a rock, and we're looking at what is the velocity in meters per second as a function of time in seconds. Velocity in meters per second as a function of time in seconds. Okay. Now, you guys know what the no air drag one looks like. Okay. And just to make sure, I mean, you guys got to know this. We just spent a few weeks on this. Okay. Everybody draw this one real fast. Right. With no air drag. No air drag. What does velocity versus time look like? And I know what's on everybody's paper. Or let's call the top of the cliff point 0. Okay, so it times 0, there's 0 velocity. I'll give you guys at least that point, right? Okay, go to the edge of the cliff, right? Drop a rock, down is the positive direction, right? Down is the positive direction. You guys all just drew that, right? Isn't that exactly what you just drew? Okay, and let's see if you guys remember this. What's the slope of this line equal to? Free fall gravity, yeah, which on Earth would be about 10 meters per second squared, right? Remember, every second that passes, it picks up another 10 meters per second. That's 10 meters per second, right? Okay, you guys remember that. Okay. Now, let's do that. The last slide that you guys were just looking at on that PowerPoint, where there is air drag. Okay. Wonder what this is going to look like. Think if you guys a head start. See if you guys can figure that out before I draw anything. You've got to have something's the same. Let's still call the top of the cliff 0.0, and let's call down the positive direction. So that point's still going to be the same, right? In fact, I bet like for the first second or so of falling, it's probably pretty closely going to match the no air drag situation. Because if it hasn't been falling very fast, it can't pick up very much air drag yet. But then the more time it's had to fall, air drag's going to pick up more and more and more. And you guys were just thinking about that situation where it actually has reached terminal velocity, right? Where all the forces balance, it's in equilibrium, it just goes down at constant velocity. Wonder how that's going to translate on that graph. See my front row right here. All right. So, all right. Alexander figured it out. Jack figured it out. I bet a bunch of guys back there figured it out too. All right. Got Scott figured it out. Bodie figured it out. All right. Yeah, I bet a bunch of guys are figuring this out. All right. All right. You guys got this. You guys are saying, well, V terminal, right? That would be like it's going to translate to like a horizontal asymptote in this graph, isn't it? Horizontal asymptote, right? And this is going to start out looking the same as the no air drag situation, okay? But then the longer it's been falling for, if you consider air drag, it's not going to pick up as much speed as fast. And in fact, it's eventually going to just hook around and reach that horizontal asymptote, and then it'll just like fall at that constant velocity until it hits the ground. It's going to kind of like curve. Like that. Okay. Now I can tell you guys the mathematics of this curve is really tricky. I saw it solved once in a class called differential equations, which you take in college after calculus 3. So, but yeah, but the general idea, right? Just the principle of like, okay, what kind of curve like that and would eventually match this asymptote. Okay, right, guys, good. All right, let's flip back over. All right, what's we got here? A boat moving through the water at constant velocity. All right, did you guys draw? This boat has a weight. Did you guys draw? Ooh, what force is holding it up? How about, yeah, force from the water. I could call that a buoyant force, right? Like a buoyant force. Did you guys draw? See, moving through the water, constant velocity. I mean, if it's moving through the water, it's going to be like a drag force from the water. It's going to be pretty significant. You can't really ignore that. So it's probably being propelled at the same time. Right? You guys think there's like an applied force and a drag force, maybe like from the propellers and onto the water, and then the water pushing back on it. Okay. Those are balancing out. Some version of that, right? Okay, guys good there? Since I'm sort of bringing up buoyant force, let me flip the screen over again and do let's do this with you guys. Okay. So I don't know if, how many of you guys quite got to this one, but if you didn't, that's right. But there was one where I had you guys hang a weight on a spring scale and then dunk it in water. Okay. Whether or not you got to this, what do you think would happen to the force rating? Suppose this weighed like 10 newtons hanging in the air. What do you think it looked like dunked in the water? Do you think the force rating probably went down to? Okay. Yeah, it's like not as much, right? Maybe it showed like 8 newtons or something. Okay. And since the lab weights are really dense, this was kind of a subtle effect. But the less dense material that you had to work with, this would have been more pronounced. In fact, if you had like a styrofoam lab weight or something crazy, then the force would have gone all the way down to 0, right? Because it would just floated. Okay. Well, let's do a quick free-body diagram for that situation. Let's do both of them side by side. Okay. So you got spring scale here, and spring scale here. Okay. So there's our setup. Okay. Whoops, sorry. One more thing. Put this one in some water. It's in the water. All right. What do these two look like side by side? So I'm thinking that this one is going to have a weight acting down. Maybe I'll just call it mg for weight. F sub g. Okay. Do you think there's a force from the spring scale pulling it up for spring scale? Okay. And those are just going to be balanced, right? So this might be like 10 newtons and 10 newtons. Right? But if you dunk this in water, it'll look a little different. I might still have the full 10 newtons acting down, the full weight acting down, right? But now the spring scale not pulling up as much because there's also an F sub B buoyant force. Oh, and whenever you have like 2 forces acting in the same direction, you do a little side action and then up, little side action then up, just to so they don't overlay right on top of each other. Okay. Hey, do you guys think this 8 plus this 2 adds up to this 10 down? Right? So that 8 plus 2 minus 10 is still 0, still in equilibrium. You guys good there? All right. Switch back over. Ooh, here's a good challenge. Can you draw 3 forces acting on an object so that the object is in equilibrium? I guess I just gave you one of the answers, didn't I? Oops. Can you guys think of maybe some other creative ways to do that. Got three forces in equilibrium. All right, so there's probably 100 different solutions to this. Let's look at two. Did you guys do? Hey, you know what that one reminds me of? Do you guys remember doing here, if you flip that one upside down, does that look exactly like you guys did with the spring scales back about a week ago? Remember that? Okay, had them at 120 degrees, 120 degrees, 120 degrees, right? Or you have the three-way tug of war, right? You could do that. That could be one way. Okay. Or hey, something like that. Right. And actually, if you flip that one upside down, it looks pretty close to what I just showed you with like the buoyant force situation, right? Spring scale and a buoyant force. Okay. Okay. So there's two ways. I just did another way on the notes on the projection. Right. It's probably a bunch. Parachuter before terminal velocity. You guys basically have this one already, right? So this guy has a weight acting down, and then a drag force acting up. Okay. All right. Now this guy, is he still accelerating down? Yeah, because there's still a net force on this guy, right? So he's still falling down faster and faster, which means that drag force is going to build up, up, up. Right. Next one, parachuter at terminal velocity. Terminal velocity. So now he's just going to float down at constant speed all the way down. Right. Did you guys draw a weight acting down and a drag force acting up? You know what? Let's think a little bit more creatively about this. I wonder what could affect that drag force. Do you guys think that the size of the parachute matters? Like if you had a bigger parachute, that would matter? Okay, so that okay. Do you guys think if you had like triple the area of the parachute, that might be like triple the drag force? Probably. That would probably make sense, right? I did tell you guys it's the drag force is proportional to like the square of the speed. Right. How about the density of the air, right? Like what if that was a parachute going through the water, right? Like right versus through the air. Do you think there'd be like a bunch more drag force from the water? Ooh, definitely, right? Right. Or if we went to Mars where there's like an extremely thin atmosphere, probably not very much drag force, right? Okay. Let me okay. Write this for you guys real fast here. Let's do okay, recording. Tell you guys what it is. Okay. So parachuter. Okay, we got the weight pulling down and the F drag balancing that up. Okay. Drag force is equal to coefficient of drag times the density of the air times the area. Here's the area of the parachute times the speed squared. Okay, so he's going down at some speed, right? So coefficient of drag, this Greek letter rho is the density of the air. This capital A is the area of the parachute. Right, like this cross-sectional area right here. Okay, and this B refers to the speed that this guy is falling. So the faster he falls, the more okay. CD is the coefficient of drag. Right. I've seen different variations on that. So I was back in college, and I think if you Google this online, like some versions of this have like a 1/2 thrown in there. So anyway, some version of that. You guys at least see the proportions, right? Okay. You don't really have to like memorize that or anything, but I mean, it's good to be able to like, if you Google that or instead text it, be able to pick that apart and say, okay, I know how to interpret that, right? All right. A rocket moving at constant velocity, just 10,000 meters per second, screaming through deep space. 10,000 meters per second, screaming through deep space. Yeah. It's constant velocity. Here's free body diagrams. What kind of vectors do you care about? Do you care about velocity vectors? Do you care about momentum vectors? What kind of vectors do you care about? Force vectors. Ah, and when you see this right here, constant velocity, what does that tell you about the net force?
0.
0. Ah, so guess what the answer is?
No arrows.
Yeah, no arrows. You're looking at it. That is the answer. The answer's already up there. There's no forces. There's no forces. It's just going. Wait, what's keeping it going? Starts with an I. Inertia. You guys got it. Inertia. That's it. Inertia. All right. I think we got time for one more today. An air hockey puck moving across the surface at constant velocity. Right. So, yeah, it looks like I'm about halfway through this presentation. So I do want to do more of these with you guys, but got a pretty good start today. We'll finish on this one today. Okay. Air hockey puck moving across the surface at constant velocity. Okay. Do you guys think that there's a weight pulling it down? Right? Do you think that you guys played air hockey, right? You guys know it has all those like air jets like pushing up, right? Is there any other force? Well, let's say you've already pushed it, right? So you've already pushed it. It's already in motion. Yeah, that'd be it. No, you're all right though. If you consider like during the push, you'd have to include that. Okay. But then it would be accelerating, which would not be constant velocity. Yeah. So if it's just going constant velocity across the table, that's it. That's the answer right there. All right. That is a good pause point. Close this down.